Everybody, tonight we're trying to count the number of distinct prime factors of a very large number, namely 12 factorial minus 9 factorial. That's what this omega means. This is a prime omega function. Now, let's look at this definition. Omega of n is this strange-looking summation. Let's work a concrete example. Let's say we have omega of 440. Now, again, what this function does, literally, it counts the number of distinct prime factors. Okay, now let's work a little further here. So notice that 440 is 8 times 5 times 11, but that's the same thing as 2 cubed times 5 times 11. So you could write this as omega of 2 cubed times 5 times 11. Now, if you'll take a look at this definition directly above, this guy right here would be behaving like our n. This would be your input argument m. And notice that there's exactly 3 distinct prime divisors, namely 2, 5, and 3. So as far as the summation notation goes, 2 would divide it, so you would get a 1 right there, right? 2 would divide n. 2 is a prime number. 5 would divide n. It's also a prime number. And finally, 11 would divide n. Whoops, sorry, I'm writing the wrong, let's see here, let me erase that. Okay, that should be 1 right there. So this would be plus 1 again equals 3. Now that's a little formal. You can just say the answer is 3 just by inspection. But I just wanted you to know I'm following the summation definition where the sum end is actually 1. And so 2 divides n by appearance, 5 and 11 are also present, so you get 1 plus 1 is 3. Now you can just look at the prime factorization and write down 3, but this is the formal definition. Okay. Now this is a trivial example because 440 it's easy to ascertain its prime factorization, but 12 factorial minus 9 factorial is an awful large number. It's very big, and so we got to use some other techniques to solve that one. Now, notice this is kind of a standard technique with factorial. You factor out 9 factorial because it is the greatest common factor. Now, 9 factorial times 10 times 11 times 12 gives you the 12 factorial back here, right? And also, there's an understood 1 directly in front of this, right? A lot of people, that bothers some people, but there's a 1 right there. That's where this 1 comes from. Okay, and then when you do the arithmetic on this, you actually get 1319 right here. Now, let's see where we stand so far. Let's forget about the 1319 and note that 9 factorial would contain the prime factors 2, 3, 5, and 7. That's the nice thing about the factorial notation. These would be the only 4 prime divisors of our number 12 factorial minus 9 factorial. If you just looked at this piece right here, 9 factorial, again, 2's in this definition, 3, 5, and 7 are the only prime numbers that are factors of 9 factorial. Now, we're not saying the powers, we're just saying the prime divisors, okay? 2 is going to have a ton of powers, right? And factorial always does. But the big question is, what about 1319 here? What is it? Is it, if it's prime, we would just add 1 more to the list. If it's not, we would have to factor it in and add more than that to the list, okay? Now, there's a result here, famous result from number theory that says n is prime if n has no prime divisors less than or equal to the square root of n. Now, the contrapositive of that is n is composite if it does have a prime divisor less than n. Okay, it's composite, which means not prime. Okay, now so the square root of 1319 is approximately 36, and all you have to do is list the divisors 2, 3. Now, I say all you have to do, it's kind of tedious, but 2, 3, 5. You can tell that 2 and 3 and 5 aren't divisors of 1319, okay? Remember, the sum of the digits would have to be divisible by 3. 9 plus 1 is 10, plus 3 is 13, 14 is not divisible by 3. So 2, 3, and 5. Now, there's a test for 7. I'm just going to tell you it's not a divisor. 11, there's a test for that too, and it's not a divisor. 13. All these that I'm going to list, I'm not going to go through it, but you can check if you want. 17, 19, what's the next one? 23, and then 29, and 31. Now, y'all, this is where all the work is being done in the problem, and I'm not going to show you the work. These are divisions that you can check yourself if you want, but these are the only prime divisors less than the square root of 1319. And none of these are divisors. These are not divisors. Okay, and I'm just going to start it. You can check it. It's rather tedious to check each of them, I'll admit, but none of these are not divisors. Okay, and so what we can conclude is that we have one more in our list here. 1319 is also a prime. So where does that lead us, folks? Well, what does phi at this number do? What is that? Omega? That means that omega of this large number, which we never actually wrote out its decimal expansion, 12 factorial minus 9 factorial, omega of that number is 5. Okay, so that's the solution here. And I hadn't dealt much with this omega function, so I just thought I'd work this problem. But this number 12 factorial minus 9 factorial has 5 distinct prime divisors. And again, a lot of them are going to have exponents attached to them, but the omega function does not care about that. Prime divisors. Call it factors if you want. All right, folks, and that's it. That's the entire problem. It's more or less me just getting used to this notation. I haven't seen much of it. I know it's super popular in number theory, but it's almost trivial just to find all the prime divisors of this. But it's a little bit of nice algebra and some work right here. And again, I did not show the work that all of these. This is what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these. And none of them, you can check them all if you want. It's pretty easy to see 2 through 11 aren't. Then after that, you just have to do the work. I don't know any shortcuts. You just do the long division, 13 into the number, 17 number, and so on. And you'll find out that they all leave remainder. So anyway, that's the answer to the question. This is equal to 5. Good night.